Hi, we're here at Riken in Saitama, Japan, just outside Tokyo, and we're going to visit with Dr. Franco Nori because we want to find out what methods he's going to be using to address some of the objectives of the new Center for Dynamic Magneto-Optics at the University of Michigan. So first of all, Franco, thanks for inviting us here on this rainy day in Saitama. But we're going to go inside and have a conversation about some of the methodologies that are used here and past experiences that Dr. Nori has had in relativistic optics. So, with our new Center on Magnetoelectric Effects and Phenomena, I'm just going to start us off here on the technical portion of this by reading a statement about some of the interests that the Center has. One of the things we're trying to do with it is develop new methods to convert light directly to terahertz radiation or electricity, to induce large magnetic fields in normally non-magnetic materials, to induce harmonic generation by magnetoelectric interactions, and also to explore the connections between relativistic and non-relativistic phenomena. And on that last point, Dr. Nori is an expert. Before we get into the technical parts, though, that he's going to help us with, maybe we should start by just having you tell us a little about your group, how many people there are, who you collaborate with typically, and how you operate here at Riken.
Well, our group has many postdocs, research scientists, and visitors. The group is combining people working in quantum optics, some of them atomic physics and condensed matter, trying to work at the interface between these three areas. So it's a very interdisciplinary group. The ability to bring visitors for a few weeks or few months visits allow us to move quickly into different directions, establish different collaborations.
It's one of the advantages of being a theoretician as opposed to an experimentalist.
So we had a good set of collaborators that has been allowing us to learn about, for instance, how to control spins in a material using optical means. Like, for instance, there are experiments done here at the University of Tokyo using a magnetic material called nickel oxide, and the question is, well, how do you control, how do you manipulate, how do you shape and sculpt the spin landscape in this material using optical pulses.
And so for people not too familiar with spin control, there normally is no direct way in which the electric or magnetic fields of light can strongly affect the orientation of spins, but some of your work has been through spin orbit coupling and that sort of thing. I want to ask you about one point that we've touched on in conversations earlier, and that is the important connection between some of that work and a recent paper having to do with the theory of magnetoelectric phenomena, where the breaking of the symmetry is a key to turning on these new phenomena, allowing them to happen, and in some cases intensifying their effects. Now you've done some work on breaking dynamic symmetries and with the magnetic field, which is what happens in some of our experiments where the magnetic component of the light breaks the symmetry. Can you tell us a little more about that work? How does the breaking of the symmetry occur in your work?
So in the past we were looking at artificial atoms, and in the artificial atoms...
Sorry, but by that you mean...
circuits, in a circuit.
Dr. Nori is an expert in the Josephson technology, so the artificial atom is referred to as
exactly, so it will be like
circuit element?
Superconducting circuits, and the Josephson junction acts like a nonlinear inductor.
Right.
So the idea there is, in the normal atoms, there are some transitions which are not allowed, because the electric dipole selection rule makes them forbidden. What we found theoretically and confirmed about 2 years later experimentally by one group in Germany and afterwards by several other groups is that you can actually introduce a magnetic field and make it possible to have transitions which were nominally forbidden before. So again, electric dipole selection rule tells you certain transitions are not allowed. By introducing the magnetic field in the appropriate manner, you can make these transitions possible by breaking the symmetry and allowing two photon, one photon coexistent transitions.
So that's actually very close to what we've discovered in the case where light provides the magnetic field, but you turn on a process which was predicted previously to be forbidden. So it's a close connection. That's one of the things that we want to leverage as part of the activities of the center. Now, I think you had some material on that topic and a few others that you wanted to present also to provide a little more detail on that. Is this a good time, or?
Yes, I wrote here a summary, and it's the following. No? The idea that the summary is that the selection rules and the dynamical symmetries can be modified by introducing magnetic field. This is work done theoretically and experimentally on a chip. And the more precisely is how to modify the selection rules and dynamical symmetries in three-level system. There's a ground state, an excited state, and a third level, auxiliary state. And so these are the systems we have been focusing on.
I'm going to draw it right here on the board while you're talking. Carry on. We'll have a three-level system here, which we can draw.
Yeah, this is called typically a lambda system because it looks like a capital lambda. And then if we have an even to odd transition is allowed, odd to even, but this one here is not allowed by the so-called electric dipole selection rule, which is written as delta L equal plus minus 1 in standard quantum mechanics textbooks. But this forbidden transition can be allowed, and it has been seen experimentally by introducing a magnetic field that plays with the symmetry. So it's a control symmetry breaking, and it's controlled via a magnetic field. So this is a common theme among the research Dr. Ran has been doing, and also us, but we've been doing it independently. And the question is, can we look together at these commonalities found experimentally in different fields, and can we learn from these results, theoretical, experimental, and how to extend them?
Yeah.
How to.
And so, just to make that point in a slightly different way, in our cases, we apply a two-photon optical transition in which it's really the electric field which provides the first step, the conjugate amplitude of the magnetic component of light for the second step, bringing you back into the vicinity of the ground state. In Dr. Nori's work, as I recall, it's two photon fields, and the magnetic field is applied externally to cause a symmetry breaking, which allows this kind of process to take place very efficiently. So with that, why don't we go to the slides?
Yes, okay. Thank you. Transitions in natural atoms. The first one is called V-type because it's shaped like a V. This is the capital lambda type, which is the one we have been focusing the most. There are ladder types. There is no delta or triangle type because of the electric dipole selection rule. So this is not allowed in natural atoms. However, these can be obtained using these circuits on a chip called flux qubits when the magnetic flux is moved away from one half. One half refers to half a flux quantum. The magnetic fields in these tiny chips are very small, so therefore forbidden transitions can be made possible by changing the magnetic field. So this is summary. In natural atoms, it is not possible to obtain the cyclic or closed transitions by only using the electric dipole interaction due to the symmetry. However, these transitions can be naturally obtained in the circuit. It's a small circuit controlled by magnetic flux because of the broken symmetry of the potential of this circuit. So a very tiny circuit is about micron level, length scale. When the applied magnetic flux deviates from the optimal point, which essentially is 1/2. So therefore, the magnetic field induced transitions in the circuit are similar to atomic electric dipole induced transitions. We published these in Physical Review Letters in 2005 as a theoretical prediction, and about 2 or 3 years later was published experimentally in Nature Physics, citing our results in the abstract. These both papers have been highly cited. Then afterwards, different experimental groups were able to confirm these predictions. Now let's look at the kind of circuits here involved. The kind of circuits, the main ingredient is a loop. The loop has 3 nonlinear inductors called Josephson junctions, and there is a magnetic field applied inside the loop. The basic idea is the following. There is a current source providing current inside the coil. The coil pumps a field on this loop via mutual inductance, and the flux, the magnetic flux, is changed by a flux quantum. So you're essentially pushing out of the loop and pulling inside the loop flux quanta. You can just forget about this, but this is the key ingredient of these tiny circuits that have these nonlinear inductors. So therefore, we're going to look at the potential energy and its symmetry. So this is the atom here. There is a kinetic energy, a potential energy. This is from here. So let's look at this potential energy in a moment. And these variables here refer to variables involved in the nonlinear inductor. So these are technical things I'm going to skip now. So therefore, we're going to look at the symmetry and parity of the potential energy. The potential energy has this form. You can choose 1/2 the flux quantum, and you see that the potential energy is an even function of these variables. That means that some matrix elements, transition matrix elements, go exactly to 0 at this value of the field, but when you change the magnetic field away from this value, is non-zero. So this is the basic idea, and this is the one that allows this 2-photon, 1-photon coexistence. So you're pumping the photons from this level to this level simultaneously, and this is what exactly the symmetry of the potential energy allows the creation of transitions which are not allowed by looking at the electric transitions. And you can actually turn them on and off magnetically, and these could be in principle used to generate photons on demand. So this is a motivation for doing this kind of control. So let's see a few examples from experiments. This one here is a controlled symmetry breaking, which involves the coexistence of 1 and 2 photon processes, and this was done in Germany. It's here is a circuit, the little tiny circuit with 3 inductors here. There is a detector, a DC squid, a resonator, an ELSA circuit. This is how it looks like. It's a very simple circuit embedded in a more complex structure. And here is the experiments and theories show clear evidence of this coexistence of 1 and 2 photon driven level anti-crossings. And this results from this controlled symmetry breaking of the system Hamiltonian, causing the parity to become a not well defined property. And this from the abstract refers to our work. We're looking at the optical selection rules in the circuits. And the question is, well, can we extend these ideas beyond the circuit? Can we allow transitions which are nominally forbidden? If you look at only the electric field, if you look at the magnetic field in new ways, can we make these transitions possible? We proposed this theoretically in 2005, and in 2008 there were the experiments by this group and there were other groups, and the prediction is the following. The prediction is that the symmetry of the potential of the artificial atom is broken, can be controlled, and a so-called cyclic, closed, or delta-type three-level atom transitions can be formed where one and two photon processes can coexist. So, thanks to.
So one of the things that I picked up on from what you just said is that the role of the magnetic field can be very important in controlling new processes. And in fact, Maxwell's equations we're normally taught to think of as being symmetric in E and B. At the same time, we're told that the magnetic field of light induces very small effects. It's not on an equal footing with the electric field at all. And this brings up another topic which I know you've been thinking about and working on, which is just that, the duality of E and B and some new advances on that topic, yes?
So we have been looking at the so-called role of the dual electric-magnetic symmetry. And then when you look at the electric field and the vector potential A, you focus on one part of the problem. On the other hand, there is an important symmetry with the so-called dual symmetry. And in the standard Maxwell equations, the Lagrangian and the tensor, the momentum energy tensors, they are not dual symmetric. It has to do with the way you split spin-orbit coupling. It's not done in a very symmetric manner. So we were looking into the problem. We did a survey, the historical problem from high energy physics and E&M, and then we were looking at the electric and magnetic fields E and B in a more symmetric footing. They naturally involve two vector potentials, the usual one A, another one C, which is essentially you take the time derivative of C and the curl of C, and you can get E and B in a symmetric manner as in A. In A you take time derivative, you get E, curl you get B, the other one C is the opposite.
But the idea is to bring the quantum mechanical formulation and relativity closer together to still be able to separate out these various momenta in a consistent fashion?
Yeah, to formulate everything relativistically and quantum mechanically in a more symmetric, consistent manner, especially the energy momentum tensor was not dual symmetric. And then we showed that by choosing a suitable Lagrangian, one can construct a dual symmetric electromagnetic field theory, preserving the symmetry between electric and magnetic properties for all the tensors. And this work was published approximately a year ago, and then and according to the Web of Science, ISI, it is that paper is considered highly cited. There is a little trophy symbol. It's attracting a lot of attention, and it's a top 1% cited paper across all papers in physics, and we just began. And there are several experimentalists right now who are interested in doing tests on this. We have been extending this to the regime of evanescent waves. We got a paper published recently in Nature Communications on how some properties which are seen naturally for propagating fields become quite different in the case of evanescent waves. And,
I remember you mentioning that at a surface, one of the effects that you're alluding to is that the linear momentum can acquire a consistent direction. It's not oscillatory, it becomes transverse and static, and this might lead to charge separation on surfaces. So it would begin to get some idea of where these new ideas are going, not just in terms of publication of new and initiation of new topics, but also how they relate to the DYNAMO project. Now I know you've also done some work on the relativistic Hall effect.
Yes.
Is this a good time to switch over?
Yes.
Maybe have you show us a few things about that topic to make it more consistent at the mathematical level.
Yes. Let me just put this into the camera here. So can you see it there well? Is it okay? Can we see? So the title of this has to do with the Hall effect. They should be going a bit down. Is it a bit down like this?
Here,
yes. Okay. Perfect. So this is the Hall effect at the speed of light. How can you demonstrate relativistic effect with your mobile phone? So therefore, what you see there is the rolling shutter effect. It's a visual distortion and vertical shift of the centroid of a rotating propeller caused by the time delay from a horizontally moving shutter camera. So therefore, it's the idea is the following. It's the Hall effects describe the interplay of rotation and linear motion in objects. There are already a number of manifestations of the Hall effect. The classical Hall effect, quantum Hall effect, spin-based Hall effect, and they all involve this interplay of rotation and linear motion. Relativity describes the effects that arise when the objects have higher speed, or they are in a Dirac cone, in a relativistic energy description. So we're looking at the Hall effect arising naturally under special relativity conditions without any external fields. We found that a relativistic treatment or rotating bodies or quantum wave system with angular momentum produces deformations and shifts in the geometric center, and the distortion have parallels to those found when recording a rotating object
in mechanical systems here from the looks of it. Yeah?
Exactly, with a rolling shutter camera.
So that's what you're saying is it's a sampling phenomenon in mechanical systems. It might be due to the periodic capture of the camera. It's almost a stroboscopic effect.
I'm going to change this one here.
So, okay.
So therefore, what you see there is a geometrical explanation of the relativistic Hall effect induced by Lorentz rotation. So the density of these helical word lines of a rotating flywheels becomes asymmetric in the moving frame. So therefore, at the bottom, you see a series of dots, and they are evolving in time vertically while rotating. So while they move up, they produce this spiral. So therefore,
it looks as though the density of the dots changes here.
Yeah, because so we have here an interplay between two effects: the rotational effect due to the magnetic field and the linear motion of particles. And these phenomena are linked with a transverse drift of the particle, which is orthogonally to both the angular momentum and the external force. For instance, in the classical and the quantum Hall effects, the electrons rotate in a magnetic field and drift orthogonally to the applied electric field. But recently, there are other Hall effects related to spin, which arise with spin-orbit type interaction, which arise naturally in relativistic descriptions between the intrinsic angular momentum of the particle and the external motion. So therefore, even though there are some differences between the system, the spin Hall effects are intimately related to universal angular momentum conservation laws. So therefore, in this case, we related this intrinsic angular momentum of the waves or quantum particles with a circulating internal current, which can originate not only from spin, but also from optical vortices and quantum vortices.
Well, for those of us who don't live in the world of quantum vortices, I think the message there perhaps is that the combination of motions, linear and circular motions that we're discussing here, can lead to very unexpected consequences, distortions of dynamics that might appear at first to be simple. But we're finding in our own work that this interplay between rotational motion and linear motion is very important. So I'm quite excited about the possible connections here with the relativistic effects you're talking about. Now, do you have more technical material to show us, or does that cover basically
I think this is the main idea, and then the rest, there are some of these videos available on our website, as you can actually, how the rotational motion combined with the linear motion can produce effects like these, which can be seen related to some sort of Doppler effect, where there is here more bunching of the objects in one direction versus moving the opposite direction. The video is very explanatory, it's on our website. The paper, I think, is clearly written, and then I think this gives the main idea.
And again, for those of you who want to make the transition from the esoteric world to the real world, if you use your own
cell phone,
digital camera or a cell phone in preview, and look at the propeller of a plane you're traveling on, you will see exactly these distortion effects. So I think with that, let's wrap it up. Yeah.
Well, thanks for coming here, and also we had Professor Kim also from. Well, we have discussed a few of the common themes and threats that could be explored. We have been working on this in parallel in different systems, and now the question is how to get this together, extend these works, make them work more effectively.
And I think it's a great opportunity to bring these separate efforts together and tie relativistic and non-relativistic optics together. So thanks for inviting us. It's been a pleasure.
It's been a great pleasure having you here.
Yeah.